Welcome to integrated circuits video. So in this we shall see triple five timer applications, the advanced video on monoshot. This is the second video on advanced topics. Because so in the previous video we were discussing about if we apply a trigger signal which is having both positive as well as negative voltage, how to get a desired pulse width. Suppose if we have this as the trigger signal which is positive and as well as negative voltages. Suppose if I pass it through this type of differentiator circuit where the product of RD into CD is less than T trigger, so that is one of the condition to get spikes at this output point. So this is what the output now. So since the resistor is connected to VCC, now this differentiated spikes is clamped to VCC and it is over VCC it is generating the spikes over here. So as you can see now, whenever there's a output change from 0 to positive, it is going to have a spike above VCC and it is going below VCC, and we should ensure that this spike voltage is going below VTL so that it can be considered as a valid trigger signal. So we know that when the voltage goes below VTL, the output of the triple five timer will go to quasi-stable state, remain for a predefined time of T. Now this T is exactly matching with the theoretical voltage because we are making sure that so trigger signal is not there for longer time. So this T is purely decided by the R and C of the external circuit. So it is not influenced by the negative level up to how long this is there in the negative voltage. Even though this is long, this differentiator circuit is generating the spike so that you are actually initiating the MOSFET, the triple five timer to go to quasi-stable state, and it is remaining in quasi-stable state for a predefined time T decided by R and C, and it comes down to stable state. Only problem here is that this positive spike is going above VCC and it is having a larger amplitude. This may affect the circuit. So in order to overcome that, the same trigger circuit is applied to a circuit which is slightly modified version of the previous one. The previous we didn't have the diode. So this diode will going to ensure that this modified trigger signal positive peak is limited to VD on. Now it is VCC plus the VD on. The spike will not go to a greater height so that it will going to affect the circuit. Now it is restricted to VCC plus VD on because the diode will be on during this cycle. Whenever it is going down, so this will go down below VTL. If it is going below VTL, we're going to get the monoshot goes to quasi-stable state and it is rest is as in the previous case. Now only difference is that here we have a diode which will make this positive swing of the spike limited to VD on. Now we shall see one more same trigger signal. Suppose if I have this circuit having a resistor and capacitor with a diode. Suppose if the amplitude of this trigger signal is bit less, so I will end up with this type of trigger signal. It's a modified version which is generating the spikes. Since the amplitude is small, you can see this spike is not going below VTL. If the spike is not going below VTL, we know that the triple five timer will not go to the quasi-stable state at all. The output remains at 0. You can see now it is always 0. Even though we think that there is a spike available which is going down, since it is not going down below VTL, so this is not sufficient to put the triple five timer monoshot to quasi-stable state. So it remains there in the stable state of 0 volt over here. So care should be taken that sufficient amplitude of the trigger signal is there so that this spike which is going negative, which is going down, crosses VTL and below VTL. Only when it is going below VTL, the triple five timer monoshot can go to quasi-stable state, remain there, and then come down to stable state. So we need to ensure that this spike is going below VTL. Okay, now we have seen the circuit diagram and all those things. Now this is the circuit diagram of a triple five timer in the textbook. Now this is a triple five timer IC diagram. So this is taken from a triple five timer IC datasheet. Now this is how the one-to-one circuit of the block diagram in a textbook and the circuit diagram in a data sheet of a particular 555 timer IC looks like. I can see you have two comparators. This is comparator 1, comparator 2. You have similar comparators. You have a plus minus, so that is indicated by a bubble here. So this bubble indicates it's a negative voltage, negative terminal. Here also there is one negative. You can say this is going to trigger. So the same is trigger here. The positive is this is positive. It is again called as threshold here. I can see this negative terminal of the first comparator, which is VTH written, is actually named as control in an IC. So actually, if you see this, so there are two terminals extra for this IC. So one is we have a reset. So this reset is not there in the block diagram, meaning I can able to reset the output by making this reset pin as 0. It's an active low reset. And we have one more terminal, which is this VTH. So we have a control over this VTH. We can actually modify the voltage of this VTH to any voltage which is an user control one. Now this 555 timer is actually an 8-bit IC, so which we'll be using in the lab. So it's a dual in package. Now these are the pin numbers and their function. Pin number 1 is ground, 2 is the trigger, 3 is the output point, 4 is the reset, 5 is the control voltage. This control voltage is exactly this uh, inverting terminal of the first comparator, and we have a threshold, which is the positive terminal of the first comparator. We have a discharge pin to which the transistor collector is connected, and we have a VCC to which the resistor and the remaining voltages that is required for the flip-flop and all those that is required. So we have this 8-pin DIP IC, that is dual in package IC. So one is ground, 2 is trigger voltage, trigger pin, 3 is the output, 4 is reset. Similarly, we have 5 the control voltage, 6 is threshold, 7 is discharge, and 8 is VCC. Now let us see what are the features of this 555 timer. So its features are, so timing can be from microsecond to hours. So we can make the timing, that is that on time, off time, or the pulse width can vary from microseconds to hours together. So you can able to perform either a stable or monostable operation. You can adjust the duty cycle of the output, and of course it's a TTL compatible, and output can sink and source up to 200 milliamperes of current. So when we talk about output going high, so it can drive a current of up to 200 milliampere. When it is going low, it can sink a current of up to 200 milliamperes. The applications can be many. To name a few, we have fingerprint biometrics. We can interface iris biometric. We can use RFID readers to use 555 timer. So there are so many other applications. So a few of them are listed here. So let us again have a look at the function of each of the pin, that is which is input, which is output. As you can see here, this CONT, that is control voltage, which is pin number 5. So this is for a different package. No need to look at this. So pin number 5 is actually an IO pin. So it is input as well as output. It controls the comparator thresholds. So its outputs are 2/3 VCC. So voltage at pin number 5 is 2/3 voltage, 2/3 of VCC. You can actually change this voltage also. So it is I as well as out. So I matlab input. So you can actually give the input to this, and or you can read the output from this control voltage. And this discharge, pin number 7 is discharge. So it's a output pin. It's an open collector output to discharge the timing capacitor. So whenever you have a timing capacitor, the timing capacitor discharges to ground through this pin. And we have pin number 1, which is a ground. And there are no NC lines, meaning all 8 pins are used here. And we have pin number 3, which is an output pin. It's a high current timer output signal, so it can deliver a current up to 200 milliampere. This is again an output pin. And we have a reset. So reset is pin number 4. It's actually an input pin. It's an active low reset. Reset input forces the output and discharge to go low. So meaning So when the discharge pin, when the reset pin is 0, so it actually resets the output and it makes the capacitor discharge. And this threshold is again an input, so it is end of timing input. If the threshold is greater than control, sets the output to low and of course discharge low. So meaning when the threshold voltage is going beyond the control voltage, that is when capacitor voltage is more than VTH, the output goes low. So that's what is we have learned in the previous what functioning of the stable monostable. When the capacitor voltage exceeds VTH, the output was going low. So that's what is this pin number 6. Pin number 2 is a trigger, so it is starting of the timing. So when to start the timer, it is given to pin number 2. So when the trigger is less than half of the control, because we know that VTH and VTL are exactly half to each other, and sets the output voltage high and discharge is open. What do you mean by discharge open? Discharge open means capacitor starts charging, and VCC is 8, pin number 8, and the input power supply, it can vary from 4.5 to 16 volts. So it is not only 5 volts, you can apply voltage up to 16 volts, that is 4.5 to 16. Now we shall see some simulations of the mono short using 555 timer using L2 spines. I can see this is a mono stable multivibrator rigged up using 555 timer. You can see the same pin number, the pin functions to 555 timer. Pin number 1 is ground, 2 is threshold, 3 is output, 4 is reset, and 5 is control voltage, 6 is threshold, 7 is discharge, 8 is VCC. You can see now we have connected the VCC and the reset to VCC, because reset is made VCC so that it will not reset the output, and we have given the trigger signal to pin number 2, and pin number 1 is grounded here, and the control voltage is connected with the capacitor, so that control voltage is stable at VTH, which is 2/3 of VCC, and we have this resistor R and C, which will decide the pulse width of the mono short, and third is the output pin. I can see we have a pulse with these specifications. You can have a look at what is these specifications are. Specifications of this pulsar. So initial voltage is 5. When it is when it is on, it is 0. So there's a delay of 1 nanosecond. Rise time is 1 nanosecond. Fall time is 1 nanosecond. When it is 0, it will be 0 for 0.1 millisecond, and it has got a period of 3 milliseconds. There are 10 cycles allowed in this. Meaning, let us see what is the type of waveform that we're going to get over there. So let me run the waveform. So let me run the circuit and try to see how does. Now let us have a look at the trigger waveform. So this is the trigger. It is initially high and it goes to low. It is low for hardly 0.1 millisecond and it's again going high. So now it is a typical signal what is applied for a mono short. Now let us see how does the output looks like. Now let me just put it in a different pane so that we can able to differentiate the output and the trigger. I can see this is the trigger signal. We know that when the trigger is above VTL, the output is 0. So here the output is 0. So as soon as the trigger signal goes below VTL, which is 1/3 VCC, the output is going to high state. It is remaining in this high state for a predefined time of 1.1 millisecond in this particular case. So once it goes to 1.1 millisecond, it comes down. Let us also have a look at the capacitor voltage of this timing capacitor. So let me just have, okay, this is how it is charging and discharging. Now let me just put it in a different pane, this capacitor voltage also. Now you can see this is, let me just put this trigger over there. I can see the capacitor voltage reaches 2/3 voltage. This is your VTH. The output goes to 0. So capacitor is not allowed to go beyond VTH. The output is going to 0. So actually, from the time from here to here is the pulse width, which happens to be 1.1 millisecond. Let us measure the time and then You can see the measured difference of time is 1.09 milliseconds. That's what is